back to the lecture series in nanotechnology in agriculture. So, we have talked about the characterization of the material in terms of characterizing the geometry, characterizing the size and morphology by using transmission electron microscopy, scanning electron microscopy and atomic force microscopy. You people to go through what is scanning tunneling microscopy. Of course, I will provide you in the notes what is the detail of scanning tunneling microscopy, but I just want that as an assignment for you to look into it. So, apart from it, we will be going through another physical technique, which is understanding the contact angle or understanding the hydrophilicity or hydrophobicity of nanoparticles. So, say for example, you have one kind of nanoparticle which interacts with water better as compared to the other one. How you can do it? How you can figure that out? What you can essentially do, you can do something called a contact angle measurements. So, how you do it? So this is where we were: characterization of the materials, transmission electron microscopy, scanning electron microscopy, atomic force microscopy and scanning tunneling microscopy. Now we are talking about physical properties of interaction in the polar and non-polar solvents. So, say for example, you have a particular particle. So, you make a film or you layer it with something. These are the particles you are layering on top of it like this. So, you are forming a thin layer or a monolayer of the particle. And now, and say for example, you want to use this for different kind of fertilizer release or some kind of insecticide release capsule or something. Now, once you form a layer of it on a substrate, you put a drop of water on top of it. Now, the possibilities of the drop of water will be either the drop of water will remain like this on top of it. So, for example, this is the particle layer. Okay. Okay. So, either the drop of water will behave like this, or it will be even much more something like this, or it will become like this, or it will become like this, or it will almost mix like this. So, if you look at it with compared to the base, start seeing what is the angle it is making. The angle is continuously changing, almost, and here it is almost mixing on the substrate. So, now based on this angle, you can calculate what will be its hydrophilic nature and what will be its hydrophobic nature. So, this is done with an instrument called goniometer, and this powerful technique is called contact angle measurements. And while we are saying this, there is another point which I wish to highlight here. You can change the hydrophilic or hydrophobic nature of a particle or of a material by introducing functional groups. Say for example, you want to make a material from, say, hydrophilic from hydrophobic, which is water hating. This is shown as water hating, to hydrophilic, which is water loving. What you have to do, you have to introduce in that material, you are adding multiple OH groups. These OH groups will eventually form hydrogen bonding and will lead to a material which is hydrophilic in nature. Okay. So, hydrophobicity and hydrophilicity are the functions of the functional groups which are attached to the material and which eventually decide how much it is going to interact with water. Okay. Now, after this we move on to the surface chemical properties, which includes, among the surface chemical properties, we talked about the physical. The major surface chemical property is, which is used in all surface analysis, is called XPS. So this is essentially X-ray photoelectron spectroscopy. So the fundamental of X-ray photoelectron spectroscopy is fairly simple. Say for example, we talk about an atom. Okay, so this is the nucleus where you have the proton and a neutron, and here you are having the electron cloud around it in a simplistic sense. Okay, these are the places where electrons are revolving around. Now, these electrons which are there, so they have different orbitals. We know that S, P, D, F, and likewise. These are the different orbitals where these electrons are hopping around. Now, these electrons which are hopping around at different electron cloud have different energies. So, in order for an electron, for example, I supply some form of energy out here into it, and for this to eject out an electron, for example, and this electron from here is getting ejected out, it will eject out with a unique kinetic energy, and that kinetic energy is essentially the energy at which it is being part of that atom. So you have to give that amount of energy, make it move out from it. So say for example, something is hold there with X amount of bond energy. So you have to give that minus X amount of bond energy to pull that out from that zone. That is unique. This energy with which it is coming out from that particular atom is unique. So you could develop a chart depending on element. So element, say for example, you have silver, copper, aluminium, iron, sulfur, okay, and the next column you may have the kinetic energy of emitted electron of, say for example, some specific shell we are talking about, so mostly the outermost shell. So we talk about the outermost shell. So with what energy that electron is going to come out in electron volt, okay, some amount introduced. Now say for example, you give that much energy. So I have a surface like this, so I have a nanoparticle like this which is lying there, and say for example, these nanoparticles have, you claim that they have sulfur and they have silver and sulfur, something like this. So what you will be seeing on these particles, you will have, if I represent sulfur with orange, you'll have this sulfur atom sitting out there, and you will have the silver atom which I am representing in light blue. You'll have the silver ion sitting out there. Okay, tons of them sitting like this. Okay, now if you put a beam of electron, certain kinetic energy or a spectrum of it, so the outermost electron from here will be coming out from the sulfur. This is, we are representing sulfur, and this one as silver. So the electron will be coming out from each one of them at a different electron volt, which is, of course, we are only talking about outermost, and you can go to the other one also, much more core ones, but at this point we are just ensuring the electrons are on the outermost shell. Now if you have a detector sitting out here which could measure that speed, here you have a detector, then that detector will tell you what you are seeing, whether it is silver, sulfur, or something else. So this is essentially X-ray photoelectron spectroscopy. This is the fundamental, and I want, based on this, I want you people to see any literature available online on X-ray photoelectron spectroscopy, but the fundamental of X-ray photoelectron spectroscopy is this, and it is one of the most powerful surface characterization technique by which you can do, the power of the technique is you can do a very simple elemental analysis. You can do a surface analysis. You can talk about some form of an advanced imaging or atomic imaging of materials, and most importantly, it has very, very high resolution in terms of the amount, some delta amount on the surface one can detect. You can detect a very, very trace amounts on a substrate or on a surface, and Kai Sigban won the Nobel Prize for developing this X-ray photoelectron spectroscopy theories and the instruments. Okay, so this is one of the most widely used technique, and I always will recommend you, wherever you get chance, try to explore this technique. Okay, the next in the line is, after X-ray photoelectron spectroscopy, you have XRD, where you are detecting the crystal or amorphous properties of materials, whether there are repetitive units or not. Say, for example, if you go back, nanocrystals we talk about, nanobelts we talk about, nano cages we talk about. So what will be the crystal structure, how the crystalline crystallinity will work out, whether there will be repetitive units to make crystals, or it will be much more like an amorphous where there are very little repeatability in the structure. Okay, so these kind of, whether these particles are crystalline or they are amorphous. So in order to understand that, your best bet is X-ray diffraction. D stands for diffraction. Okay, so this is where you are using X-ray for determining the, I would say, stereochemical properties, or in space how these atoms are arranged. This is the technique what you are using. Okay, the next in the line will be FTIR. Fourier transform infrared spectroscopy. So this technique gives you a knowledge. So I am not getting into the depth of the technique, which I will again leave for you to explore. This technique gives you an idea. Say for example, what are the different kind of functional groups which are present on your sample. Types of functional groups. Say for example, you are increasing the hydrophilicity of the particle. So what are the kind of functional groups which are present, and all these details that you can obtain using Fourier transform infrared spectroscopy. This is the power of the technique. So if we had to summarize what all you can do from this, this includes your, in the surface chemical techniques, you have XPS, you have XRD, you have FTIR. Prior to that, you can do the physical properties, you can figure out in terms of their interaction with water. You can figure out the hydrophilicity and hydrophobicity of the surface using contact angle measurements and using the instrument called goniometer. Apart from it, in order to figure out the geometry, size and morphology, you have transmission electron microscopy, you have scanning electron microscopy, you have scanning tunneling microscopy, and you have atomic force microscopy. So to summarize this part, what we covered here is classification of nanomaterial in terms of shape and geometry, chemical nature in terms of chemical nature, the organic nature, inorganic nature, and carbon-based nature. Then we talked about the synthesis, where we talked about physical, chemical, and biological, and followed by that we talked about the characterization of nanomaterial in terms of figuring out the shape and geometry using different form of electron microscopy and AFM and STM, which includes SEM and TEM. Then we talked about all the chemical ways of understanding the atomic architecture using XPS, XRD, and FTIR. And then we talked about the water heating and water loving properties in terms of contact angle. So that kind of covers our basic understanding of nanotechnology, which will be needed to understand this course in greater details of how basically all the synthesis processes are taking place and how these synthesis could be done and what are the basic absolutely fundamental requirements for you to document your work in terms of how you classify your material, how you synthesize your material, and how you characterize your material, and then of course introducing it to its agricultural relevance. Okay. So, based on this framework, we will start our journey of different kind of nanomaterials which are currently under intense exploration for their application in increasing agricultural productivity, water purification, and myriad of other applications. Thank you.